see the echo-planar imaging. A phase encoding gradient process typically fills one line in the K-space. Okay? So one phase encoding gradient, we can have just one MR signal. Okay? So to generate an MR image for a specific slice, many phase encoding gradient process, usually we use 256, are required. In the EPI technique, on the other hand, a single excitation pulse generates enough MR signals to fill the K-space for an MR image. So this means that just one single excitation pulse, we can have 256 MR signals to fill the K-space at once. An MR image can be obtained in as little as 20 to 100 milliseconds if the EPI technique is applied to the spin echo and GRE per sequence. So we just need 200 milliseconds for one image. As a result, the EPI technique is used in fMRI and perfusion measurements, both of which need faster imaging. The EPI technique, on the other hand, necessitates hardware for fast gradient direction switching and precise gradient slope control. So previously we discussed gradient echo GRE per sequence and FSC, fast spin echo per sequence. So in those cases, we use the software. On EPI technique, we need the hardware because we have to change gradient direction very fast, and also we have to control the gradient slope very slightly each time. So for this purposes, we need some hardware to do this in the faster processing. First, let's see the EPI technique is applied to the spin echo per sequence. So EPI spin echo per sequence. The figure depicts an example of the EPI technique being applied to the spin echo per sequence. Precoding gradients for both X and Y directions are applied between 90 degree and 180 degree pulse, A to B. This. So this X direction and Y direction. To detect MR signals, phase changing phase encoding and frequency encoding gradients are applied at 180 degree pulse. So after 100 degree pulse, we used fast changing phase encoding gradient and frequency encoding gradient. Okay. For simplicity, the figure depicts the process of applying just 11 gradients to produce MR signals. We just see 11, right? 11 phase encoding gradient and 11 frequency encoding gradient. Normally, we use the 256 gradients. So we use if we use 250 steps, then just one TR we can get enough MRI signals to obtain the image. Although frequency encoding gradients are sinusoidal, there's a sinusoidal frequency encoding gradient. Phase encoding gradients are blips. These blips are applied when the frequency encoding gradient reaches 0. So at this point, so frequency encoding gradient is at 0, then a blip type phase encoding gradient is applied. Okay. So at this moment, phase encoding gradient. So when the frequency encoding gradient reaches 0, then the blip type phase encoding gradient is applied. Okay. At the center of the phase encoding gradient, MRI signals are detected. So here, at the center of phase encoding gradient, the signal is detected. Just the same position. After 90-degree pulse, spins decay with T2 star relaxation and are replaced by 180-degree pulse. Okay. Okay. As a result, we time the application of gradients so that MR signal reaches its maximum value at phase encoding gradient center. Yeah. Center here. Okay. After initial strong negative phase encoding gradient, this phase encoding gradient, the largest, but this phase encoding gradient will become negative due to this 180-degree pulse. So in this graph, in this figure, phase encoding gradient is positive, but becomes negative due to the 180-degree pulse. So we can infer that at this phase encoding gradient, it has largest negative phase encoding gradient. And then positive phase encoding gradient is applied in this process. So subsequent weak phase encoding gradient flip, just flip type of phase encoding gradient gradually increase the phase according to 0. So the phase is negatively largest, and the phase is increasing, right? Due to this blip type phase encoding gradient. Okay. So if we have 256 phase encoding gradient, then for each time the phases are different. Okay, so we have 256 different phases on the signal, so which corresponds to the TE. Phase encoding is increased incrementally by the further phase blips. So negatively largest phase, and this blip type positive phase encoding gradient, so phase is increasing and passing to 0 and further increasing. So we have 256 different phases. So we have 256 MR signals at different phases, right? The 256 different phases. Now let's see how the signal fill the K-space in the EPI spin echo. After 90-degree pulse, K changed from A to B through the positive precoding gradient in the A to B process. So A to B process is GY and GX, so X direction, Y direction. Okay. So this is positive, and this is also positive. So starting from the origin to A to B process, Kx becomes largest value, positively largest value, and Ky also becomes positively largest value. So point B is here. Okay. So following that, K flips its signs to negative due to 180-degree pulse. Due to this pulse at this position, the sign of Kx and Ky are reversed, right? So Kx max, Ky max will become minus Kx max and minus Ky max at this point C. Okay. So B to C. The first frequency encoding gradient is then applied, resulting in an increase in Kx. So this one, positive frequency encoding gradient. So Kx will increase following this path. Okay. Since no phase encoding gradient is used in this process, Ky remains the same as before. So this line. This process corresponds to C21 line. When the frequency encoding gradient reaches 0, a blip type phase encoding gradient is applied. So at this point, the frequency encoding gradient is 0. So blip type phase encoding gradient is applied. So that means Kx remains the same, but Ky will increase a little bit, moving to the positive direction. So this is equivalent to K moving up along the Ky direction without changing Kx. So phase frequency encoding gradient is 0, so no change in Kx. But due to this blip type phase encoding gradient, this line will go up. Next step is to apply negative frequency encoding gradient. This negative frequency encoding gradient. So it's moving to this direction. Okay. So in this process, Kx moves in the minus x direction to minus Kx maximum without changing Ky. Okay, so moving this direction. At this position, a blip type frequency encoding gradient is applied, so the Ky will increase due to this blip type phase encoding gradient. And then pulse encoding gradient is applied, will move in this direction. So in this way, in zigzag way, the K space is filled. So if you use 256 process, then we can have 256 MR signals at once, at 1 TR time. Okay. As seen in the figure, successive operations of the above gradient patterns will the K space, fill the K space in a zigzag pattern. One excitation of pulse can produce MR signal if 256 steps, few steps. In this figure, we just gave the just 11 process, but we can extend this to 256 steps. Then we can get enough MR signals to make an image, MR image, using one excitation pulse, this pulse. Now let's see the EPI-GRE pulse sequence. The EPI process is used to the GRE pulse sequence shown in the figure. One excitation pulse can fill 256 lines in the K space to generate an MR image. After the initial strong negative phase encoding gradient, this one, subsequent weak phase encoding gradient blips, this blips, gradually increase the phase encoding gradient to 0, which corresponds to the effective TE. So at this point, phase will become 0. So negatively largest and passing this 0 position and increasing. Okay. Phase encoding is increased incrementally by the further phase blips corresponding 250 phase encoding steps. So we can achieve 256 phase encoding steps using this kind of blipped phase encoding gradients. After alpha pulse, partial angle pulse, K changes from A to B through the negative precoding gradients and the A to B process. So this is negative and this is negative. So starting from A after B, at this point, at B, Kx will become maximum minus maximum, and Ky will become minus maximum. So this position, so A to B is posing in this way. There is no gradient between B and C in this interval. Thus B and C are at the same position in the K space. The first pulse encoding gradient is then applied, resulting in an increase in Kx. So this first phase encoding gradient increase Kx without changing ky, so moving in this direction. Okay. Since no phase encoding gradient is used in this process, ky remains the same. So we are moving in this direction. And at this point, 1 here, Physics encoding gradient is 0, and the flip of phase encoding gradient is applied, so y direction, so moving up due to this flip phase encoding gradient. So this process corresponds to C21 line. Okay. Oh, no, this C21 line, and when the frequency encoding gradient reaches 0, so here, a flip type phase encoding gradient is applied. So this is equivalent to k moving up along the ky direction without changing kx. So this direction. The next step is to apply a negative frequency encoding gradient, this one, and we are moving in this direction. In this process, kx moves in the minus direction, minus kx direction, to minus kx maximum here, without changing ky, slow phase encoding gradient. As seen in the figure, successive applications of above gradient patterns filled k-space in a zigzag pattern. So continuously we can fill k-space. So one excitation pulse can produce an MR image if 256 steps are utilized instead of 11 as shown in the figure. So we are using 11 for simplicity of the figure, but we can use 256 steps. Then we can have 256 MR signals instantly at once, so we can obtain an MR image just for one excitation pulse. And scan time for an MR image becomes very short. There are several patterns which are used clinically. Several alternative fast k-space mapping methods have been developed. We can accomplish spiral-shaped k-space filling and significantly shorten MR imaging time by applying sinusoidal gradients with increasing slope in the EPI process. So using this phase encoding gradient and Physics encoding gradient, so the sinusoidal patterns of gradient, and its amplitude is gradually increasing. Then we can fill k-space in this way, spiral or shape filling. Because of T2 star relaxation, the signal's amplitude diminishes over time. So according to time, the signal intensity decreases very fast according to T2 star relaxation time. So the spiral-shaped process can provide initial signal with large amplitude in this position. resulting in well contrast MR images. Okay. So intensity of these MR signals is largest at the center and the K-space. So if we use this spiral type mapping, we can get the MR signals first, the center of the K-space. So as time goes on, we can get the out signal. So the center signal has largest intensity, so we can get well contrast MR image using this spiral type mapping process. The K-space is filled radially by employing phase and frequency gradients with linear relationship. So we can fill the K-space radially in this direction. This technique also quickly fills K-space. So there are various types of mapping methods. So we can use this mapping method to decrease the imaging time. Now let's see some example regarding what we discussed so far. For example 1. Find the expression of the MR signals and subsequent GRE per sequence. So there's 3 GRE per sequences, and each process we can get the signal. So find the expression for each signal. That is question A. Which pulse angle produces the strongest signal? So if we change the partial flip angle, then which pulse angle produces the strongest signal? The earliest angle is the name given to this pulse angle. At point 1 here, that's M0, right? Longitudinal magnetization has its largest value, so that's M0. And there is no transverse magnetization at point 1, so MXY equals 0. At this point, point 2, we use the pulse of angle alpha, so longitudinal magnetization will become mg1 cosine alpha, right? So we used angle alpha, so the longitudinal magnetization will inclined in this direction with the angle alpha. So mg longitudinal magnetization will become mg cosine alpha, and transverse magnetization will become mg1 sine alpha, right? And now at point 3 here, longitudinal magnetization is recovering, right? Recovering during time tr. The starting point is point 2, right? Point 2. So mg, we have this relation. So we mg3 here, at this point. Longitudinal magnetic recovery from mg2. The time interval is tr. So you can get this expression. And mg2 is given here. So you can put here, and then we can have this expression. Okay. And T2 is much shorter than TR. TR is TR. So MXY transverse magnetization disappears, right, during this time, TR, because T2 is very short than TR. Now at this point, mg4, we use the angle alpha pulse, so mg3 cosine alpha and mg3 sine alpha. Instead of previous procedure, we have lots of time to do this process. So instead of that, we suppose that there were multiple pulses before point 1, and so the equilibrium was formed. So we can suppose mg3 equal to mg1. So there are several processes before all this, so equilibrium was reached. So mg1 here, 3 will become the same for equilibrium. So in this condition, we can have mg3 equal mg1. mg3 was given this value, mg1 is m0 cosine alpha, so we can get this expression for mg1. Now let's verify that this is correct form. To do this, we put the alpha equal 90 degrees. So instead of alpha angle, we put the alpha 90 degrees. Okay, so here 90 degrees. Then this will be 0. So mg equal this one. So this is correct expression, right? Which is correct result for spinel pulse sequence. So we can verify the Laguerre relation. Okay. So here we have signal, first signal. So xy2 equal mg1 sine alpha due to this angle alpha pulse. So this is the first signal, right? So mg1 is given here, so we can put this one here. Then first signal will become this expression, signal intensity at point 2. So this is the first signal. Actually, the signal is detected TE after the pulse, or in the GRE pulse sequence. As a result, T2 star relaxation reduced the signal intensity. But in GRE pulse sequence, alpha is very small, so we can get this term 1. Okay, so this we can there, you can assume the first signal has this form. Okay. And the question B, find the largest signal intensity angle. So we differentiate this signal according to alpha, and if we do put the 0, then we can get the largest angle by this form. Okay. Next example. Determine the largest angle in the case of T1 equal 1000 millisecond and TR equal 100 millisecond. Okay. So we already obtained the expression for the largest angle, which was given by this form. So we know TR and T1. So largest angle will become 25 degrees. Okay. Next question. Determine the ratio of the largest angle signal intensity to the 90-degree pulse signal intensity. Okay. For 90-degree pulse, mg equal about 0.095 m0. Okay. And largest angle pulse, we have expression here, signal intensity. So alpha is 25 degrees here. So we can get 0.22 m0. So the ratio with the largest angle signal intensity and the 90 pulse intensity is 2.32. So GRE pulse sequence with the largest angle has a larger signal intensity than that of 90-degree pulse. Okay, so 2 times larger than that of the 90-degree pulse intensity. Next question. Determine the signal intensity ratio between GRE pulse sequence with the largest angle and the spinnacle pulse sequence with t equals 30 millisecond and t2 equals 50 millisecond. Okay. For spinnacle pulse sequence, the signal intensity is given by this expression. So we know T1 and T2, and TR and TE is given, so we can get 0.052 m0 for spinnacle pulse sequence. Largest angle pulse sequence, we have intensity here, so we can get the ratio of GRE pulse sequence with the largest angle and the spinnacle pulse sequence intensity 4 times 2 is 3, about 4 times larger for GRE pulse sequence. And the ratio between 90 pulse sequence and spinnacle pulse sequence is also 90-degree pulse sequence has a larger signal intensity than that of the spinnacle pulse sequence. Here's expression, explanation because we have why we have this kind of signal intensity ratio. The spinnacle pulse sequence has using the TE. TE is much larger than that of the GRE pulse sequence. Okay, so the spinnacle pulse signal is smaller than the 90-degree pulse and Ernst angle pulse signals, since it is detected TE after the pulse has opposed to the 90-degree pulse and Ernst pulse signals, which are detected immediately after the pulse. Spherical pulse sequence TE is much larger than that in the GRE pulse sequence. Okay. So T2 relaxation thereby reduced the spin echo signal. Yet even in the GRE pulse sequence, the signal is detected TE, much less than that in the spin echo pulse sequence after the pulse, and the signal in the GRE pulse sequence was reduced due to the T2 relaxation. So the reason why GRE pulse sequence intensity is larger than that of the spin echo pulse sequence is that the TE in the spin echo pulse sequence is larger than that in the GRE pulse sequence. Okay. So we have this factor in the spin echo pulse sequence, exponential minus T over T2. So due to this factor, the signal intensity in the spin echo pulse sequence is smaller than that in the GRE pulse sequence or 90-degree pulse sequence. Okay. Next example. For the spin echo pulse sequence with the parameters TR equals 3000 millisecond, NX equal 1, and NY equal to 156, determine the scan time. So scan time is TR times number of phase encoding gradients and number of excitation. Is 1, right? So we can get the scan time is about 12 minutes. Okay. What is the FCE pulse sequence's scan time under the same condition as the spin echo pulse sequence? Use ETR equal 8. So 1/8 of time this time, so that's 1.6 minutes. Next example. Determine the 3D GRE pulse sequence's scan time. Here are conditions: TR equals 30 millisecond, NY equal to 256, number of excitation equal 1, and NG equal 60. So we have 60 slices. So that gives about 7 minutes. Also compared to the scan time of the spin echo pulse sequence, for one image, spin echo pulse sequence, we need about 12 minutes. But for GRE case, 3D GRE case, if we obtain the 60 slices at once, but time scan is just 7 minutes. Comparing these two values, we can get GRE pulse sequence has very small time for one image. Final example. Depending on their surrounding material, nuclear spins have slightly different Rameau frequencies. The resulting artifact in the MR image is known as chemical shift artifact. Nuclear spins in water have a Rameau frequency that is about 3.5 ppm greater than spins in fat. First question, find the difference in Rameau frequency between the spins of fat and water in the 1.5 Tesla field. Normal frequency is given by this expression. So we can get just 1.5 Tesla. So we can get 64 megahertz. And the difference between the ground frequency difference between the spins in water and the fat is about 34.5 ppm. So we can get the ground frequency difference by multiplying 3.5 ppm to this normal frequency. Then the frequency difference can be obtained 220 Hz. So normal frequency difference between spins in water and fat is about 220 Hz. Okay. Next question. What is the bandwidth of the MRI signal if total sampling time is 8 milliseconds? We have total sampling time, so we can get the bandwidth with this value. So the bandwidth is 32 kilohertz as put into 256 pixels. So 1 pixel is equivalent to the frequency of bandwidth divided by 256. So 125 Hz. Okay. Using this 8 millisecond, we can get the bandwidth, right? Bandwidth equal 1 over delta sampling time, right? So we can get, we have TS, total sampling time. So TS equal NY times delta TS. Okay. So NY equal 256, NX equal NY, so 256, and the TS total sampling time is 8 milliseconds here. So we can get delta TS, right? So that's for the year. Then we can get the bandwidth. So that is 32 kilohertz. Okay. And 1 pixel is this whole pixel. So 56 pixels. We have bandwidth, this bandwidth, and 1 pixel is equivalent to the frequency divided by NX. So we can have 125 Hz. Okay. So normal frequency difference of 220 Hz, this difference amounts to approximately 2 pixels in terms of pixel count. Okay. So this question already obtained here. So C is the frequency difference between the spins in water and the fat caused by chemical shift corresponds to how many pixels? So we obtain 2 pixels. What is the position movement of the water in the fat? In the image, if the pixel size is 2 millimeter. So pixel size in the image plane is 2 millimeter. So in that case, 2 pixel corresponds what centimeter or millimeter. Okay. So position movement in the image is 4 millimeter because 2 pixels, and each pixel has dimension of 2 millimeter. So totally a 4 millimeter movement due to the number frequency difference. Okay, so there are 2 pixels, and each pixel has a size of 2 millimeter. So 2 pixel corresponds so to 4 millimeter. So the position movement in the image is 4 millimeter. Okay. This gives the 3D GRE and additional phase encoding steps in G-axis. Okay. So G-axis. So scan time, we have to multiply NG here. And for sequence is given by given in this figure. 3D for sequence, we have slice selection gradient for 3D image is included here. Others are the same, but the slice selection gradient series should be included here.